Hello everyone. So, in last lecture we discretized stream function equation and vorticity transport equation using finite difference method. So, both the equations to discretize the both the equations we used central difference method. So, the order of accuracy was delta x square delta y square. Today we will consider two problems. First we will consider lead driven cavity problem, then we will consider flow between parallel plates, plane Poiseuille flow, and we discuss about the boundary conditions. So, our governing equation is stream function equation del 2 psi by del x square plus del 2 psi by del y square is equal to minus omega, where omega is your vorticity and vorticity transport equation is u del omega by del x plus v del omega by del y is equal to nu del 2 omega by del x square plus del 2 omega by del y square. So, now we will derive the boundary conditions for lead driven cavity problem. So, first let us discuss what is lead driven cavity problem. Lead driven cavity. Okay. So, we have enclosure, square enclosure. Okay. So, it is a square enclosure filled with some liquid, okay, some fluid. So, inside some fluid is there, and this is your square enclosure. So, let us say this is your L and this is also L, square enclosure, and the upper bound, this upper surface, okay, it is connected with some belt, let us say, and this lead, this is upper plate. So, this is moving with some velocity. Okay. So, this belt is moving like this. So, you can imagine that this boundary is moving in x direction. So, if it is x and this is your y, then along x direction this lead is moving with some velocity u. So, you have enclosure, square enclosure, left, bottom and right surfaces are having no slip boundary conditions, those are stationary walls, and the top wall is moving with velocity u. Okay. So, in terms of velocity boundary conditions, what are the boundary conditions? So, in terms of velocity boundary conditions, so here u is equal to v is equal to 0, the left boundary also u is equal to v is equal to 0, and right also u is equal to v is equal to 0. So, all are no slip condition. Here also it is no slip condition on the top wall. So, it is u is equal to capital U, because it is moving in the x direction with a velocity capital U, and v is 0. Okay. So, we have applied no slip boundary conditions in all four walls, and this is your left wall. So, this is your left wall, this is your left wall. So, this is your left wall, okay. This is your right wall, this is your bottom wall, and this is your top wall. Okay. So, if you write the boundary conditions mathematically for velocities only, then boundary conditions for the problem lead driven cavity. Okay. So, you have left wall, you have u is equal to v is equal to 0, right wall u is equal to v is equal to 0, bottom wall is u is equal to v is equal to 0 and top wall u is equal to capital U and v is equal to 0. Okay. So, these are the boundary conditions in terms of velocities, but we are solving the governing equations for psi, which is your stream function, and vorticity omega. So, we need to know the boundary conditions in terms of psi and omega to solve the discretized equation. So, first let us find the boundary conditions for psi, okay, stream function boundary condition. Boundary condition for psi, okay, psi is stream function. So, we need to find what are the boundary conditions for psi. So, to find the boundary condition for psi, what we will do, first we will impose the normal velocity at each boundary and we will find the boundary condition for psi. So, if we consider left wall, what is your normal velocity? Normal velocity will be u, v is your tangential velocity, because if this is your x direction you have velocity u and in y direction you have velocity v. So, if you consider the left wall, then left wall the normal velocity is u. So, you put normal velocity as 0, that means u is equal to 0. Okay. So, now you write u in terms of stream function, okay. So, that you know. So, the gradient of stream function with respect to y will be 0. So, that means del psi by del y will be 0. So, you can see, so this is your y, right, in this direction it is y. So, along this your the gradient of psi will be 0. That what does it mean? It means psi is equal to constant, okay, psi is equal to constant, let us say some constant C1. Okay. So, from this del psi by del y is equal to 0, if you integrate it, then you will get psi is equal to C1, C1 is some constant. Similarly, for right wall, what is the normal velocity u, okay, u is equal to 0. Similarly, del psi by del y is equal to 0 and you can write psi is equal to C1 or psi is equal to some another constant, let us say psi is equal to C2. Okay. And if you write the, so on the right wall psi is equal to C2, another constant, let us say. Okay. Now, bottom wall. Okay. So, for the bottom wall, if you see here, so normal velocity will be in y direction, that means v is equal to 0. So, you can write v is equal to 0 and v is in terms of psi, it is minus del psi by del x is equal to 0. Okay. And you can see, so along x it is 0. So, psi is also on the bottom wall will be constant and let us say the constant is C3. Okay. Similarly, on the top wall, okay, if you consider top wall, what is the normal velocity? V is equal to 0, okay, and you can write minus del psi by del x is equal to 0. Okay. Why? Because u is del psi by del y and v is equal to minus del psi by del x, you know, right. So, minus del psi by del x is equal to 0. So, psi is equal to C3. So, from the normal velocity boundary conditions, we have found that in all boundaries you have some constant streamlines. Okay. So, constant stream function, constant stream function. Okay. So, left wall is C1, right wall is C2, bottom wall is C3 and top wall is C4. Now, you see, so these walls are connected, right. So, now the constant stream function denotes the streamline, right. We know that constant stream function is a streamline and two streamlines cannot cross each other, right. That means, you have So, if you see right wall left wall, so in the left wall, so this is continuous and to the bottom walls, in bottom wall to right wall and right wall to top wall and top wall to left wall. So, these are all connected. What does it mean? That means it is a single streamline and the stream function should be same. So, along all these 4 boundaries psi will be constant. So, you can write psi is equal to C for all 4 boundaries. Okay. So, that means psi is equal to constant and it is the same constant, okay, because 2 streamlines cannot cross each other. So, obviously, it should be a continuous. So, that means psi is constant single value in all 4 boundaries, and for simplicity let us take that psi is equal to 0, this constant value is 0 on these 4 walls. So, we are considering psi is equal to 0 for all 4 boundaries, because we are considering that constant C as 0, because it does not matter, right, because you can take any constant, okay. So, it will not affect your solution. So, we are considering the stream function value on the walls as 0 and accordingly your stream function value will be there at the interior points. So, now let us find the boundary conditions for vorticity. Boundary conditions for omega. Okay. So, we know that omega in terms of stream function. So, minus del 2 psi by del x square plus del 2 psi by del y square, okay. And you have this square enclosure, okay, top wall is moving and psi is equal to 0 we have considered, okay, on 4 walls, okay. And let us say that you have the values I is equal to 1 to m and 1 to n, okay. So, I is equal to 1 to m it is varying and j is equal to 1 to n, okay. So, I is equal to 1, that means it is j is varying. So, it is a left boundary and I is equal to m, okay, and j is varying. So, it is your right boundary, okay. So, now let us consider left wall. Okay. So, in the left wall if you consider, so what is normal velocity? Normal velocity is u is equal to 0, that means del psi by del y will be 0, okay. So, on the left wall del psi by del y is 0 and you can see that psi is constant along this line, right, along this line. So, its gradient is 0 and its second derivative also will be 0. So, if you take the gradient of del psi by del y, that will be also 0 along this line. So, del 2 psi by del y square will be 0, okay, because it is constant, there is no variation and its gradient is 0 everywhere. So, obviously, if you take the derivative with respect to y of this gradient del psi by del y, that will be also 0 along this left wall. So, del 2 psi by del y is 0. So, now you can see this equation, vorticity equation. So, if you put del 2 psi by del y square is equal to 0 for the left wall, so omega will be minus del 2 psi by del x square, okay. So, now you use central difference method to discretize this second derivative. So, if you use second derivative, so it will be, so now you can write omega for which wall? Left wall, where I is equal to 1 and j will vary, okay, j will vary, okay. So, omega 1 j will vary from 1 to n. So, for this it will be now minus second derivative. So, you discretize using central difference method. That means, if you have what we will do. So, if this is the left boundary, so it is your I is equal to 1, we will take a fictitious point outside this boundary. Okay. So, this is your one grid and this is your interior grid. Okay. So, this is your fictitious point. Okay. So, here you have I is equal to 1, here I is equal to 2 and this is I is equal to 0. Okay. So, and this way it is, if it is j, so it is j plus 1 and this is your j minus 1. Okay. But it is del 2 psi by del x square. So, it is be for a point j only. So, you can write with this fictitious point. So, I is equal to 0 is fictitious point outside the boundary and with the same distance delta x. Okay. So, this is also delta x and this is also delta x. So, if you consider this, then you can write discretized form of this second derivative as psi. So, 2j minus 2 psi 1j plus psi 0j divided by delta x square. Okay. But we do not know the value of psi 0j because it is a fictitious point. So, to find the value of psi 0j, we will use the another velocity boundary condition which is v is equal to 0. So, you know that on the left wall v is equal to 0. What does it mean? Minus del psi by del x is 0. That means, del psi by del x is 0. Okay. So, if del psi by del x is 0, so you can write the central difference. Okay. So, psi 2j minus psi 0j divided by distance between these 2 points 2 delta x. Okay. Because here I is equal to 2 and I is equal to 0. So, 2 delta x is equal to 0. Okay. So, we have used central difference. So, now psi 0j you can find as psi 0j is equal to psi 2j. Okay. So, now psi 0j value you know. So, you put it in this expression. So, you will get psi omega 1 j is equal to minus psi 2 j minus 2 psi 1 j and this is also psi 2 j divided by delta x square. So, that means you can write as minus 2 by delta x square psi 2 j minus psi 1 j. Okay. So, psi 1 j where it is psi 1 j on the boundary. Okay. So, if you assume psi is 0, then you can put it 0, but if you can take, if you consider some other values, constant values on the wall of psi, then psi 1 j will be having some constant value. So, we are not going to write 0 here because how you are considering the constant, depending on that psi 1 j value will depend. So, that means if you consider trim function on the walls, then it will be 0, and if you consider some constant value, then you can put it that constant value here. So, we are not going to put it 0 here. So, let us keep in terms of psi 1 j. Okay. So, omega 1 j we have found. Similarly, now you do for the right wall. Okay. So, right wall also. Okay. So, for the right wall, so if it is right wall, okay, so I is equal to m in this case, and you have this is your original interior grid and this is your fictitious grid outside the boundary. Okay. So, you can see this is your I j, this is your I plus 1 j and this is your I minus 1 j. So, I minus 1 j means m minus 1 j, okay, and this is your I plus 1j means it is your m plus 1j, and this is your mj, okay, this is your mj. Okay. So, similarly we will use the normal velocity. So, normal velocity is u is equal to 0. So, del psi by del y is 0 and del 2 psi by del y square is equal to 0, and from the vorticity equation you can write omega is equal to minus del 2 psi by del x square. Okay. Now, if we discretize it, so you will get omega mj on the right wall is equal to minus, now central difference we are using. So, you can write psi m plus 1 j minus twice psi mj plus psi m minus 1 j divided by delta x square. Okay. Now, psi m plus 1 j is unknown because it is a fictitious point value. So, we will use again the tangential velocity v is equal to 0, del psi by del x is 0, and if you discretize it. So, you will get psi m plus 1 j minus psi m minus 1 j divided by 2 delta x, because we have considered at the same distance this fictitious point. So, 2 delta x is equal to 0 and psi m minus 1 j, sorry, m plus 1 j which is outside the boundary is equal to psi m minus 1 j, and this value if you put it in this omega expression, then you will get omega m j is equal to minus, so it will be psi m plus 1 j minus twice psi m j and plus psi, now sorry, this m minus 1 j you just write, because now you are putting the value of psi m plus 1 j as psi m minus 1 j, here m minus 1 j divided by delta x square. So, you are going to get omega m j is equal to minus 2 by delta x square psi m minus 1 j minus psi m j. Okay. So, in this case again psi m j actually the values of psi on the right wall, and if you choose 0 then it will be 0, otherwise it will have some other value. Now, let us consider the bottom boundary. Okay. So, similarly we will consider the fictitious point outside this bottom wall, and first we will make the normal velocity 0. So, for the bottom wall, okay, so normal velocity is, so this is your bottom wall, okay, and you have the fictitious point outside. So, this is your grid, okay. So, this is your j is equal to 1. So, it will be I 1, this is your I 0 and this is your I 2. I 2 is the interior point, I 1 is the on the wall, and I 0 is the fictitious point outside the boundary. So, similarly first we will consider the normal velocity as 0, that means v is the normal velocity. So, it is 0, and from here you will get del psi by del x is 0. So, you can see that along this bottom wall psi is constant, okay, psi is constant, del psi by del x is 0, and obviously del psi by del x is 0 everywhere. So, if you take the gradient of this del psi by del x with respect to x, that will be also 0, that means you will get del 2 psi by del x square is equal to 0. So, your omega equation will be minus del 2 psi by del y square. Okay. So, now if you discretize using central difference method, then for omega I 1 you can write psi I 2 minus twice psi I 1 and psi I 0 and divided by delta y square. Okay. So, this delta y square, delta y is the constant step size, Okay. So, similarly now psi I 0 is the value of psi at the fixed point, let us find using the tangential velocity condition. So, tangential velocity is u is equal to 0, that means del psi by del y is equal to 0, and if you discretize del psi by del y using second order approximation, then you will get psi I 2 minus psi I 0 divided by 2 delta y is equal to 0, and that will give psi I 0 is equal to psi I 2. So, you can see that the Fixier's value is same as the interior point psi I 2. Okay. So, now this value you put it in the omega expression. So, you will get omega I 1 is equal to psi I 2 minus twice psi I 1, and psi I 0 is psi I 2 divided by delta y square. So, you will get omega I 1 is equal to minus 2 by delta y square. Okay. So, you will get psi I 2 minus psi I 1, and here you can see psi I 1 is the boundary value. So, for our case we have chosen as 0, but you keep it as it is, so that if you have some constant value you can use it here. So, psi I 1. Similarly, now consider the top boundary. So, top boundary. So, on the top boundary, so you can see this is your boundary, okay, and it is moving in the x direction. Okay, this is moving in the x direction with u is equal to capital U. U is equal to capital U. So, now if you take the grid, so this is your fictitious point, this is on the wall, and you have interior point. So, this is your j is equal to n, right, j is equal to n. So, it will be I n minus 1 and I n plus 1. Okay. So, similarly, now first we will use the normal velocity condition. So, what is the normal velocity condition? Normal velocity is v is equal to 0. So, normal boundary condition is v is equal to 0, that means del psi by del x is equal to 0. Okay. So, along this boundary obviously del psi by del x is 0. So, you can write del 2 psi by del x square is also 0. Okay. So, your omega condition is minus del 2 psi by del y square. Okay. And if you use central difference method, then you can write omega I n is equal to minus psi I n plus 1 minus twice psi I n plus psi I n minus 1 divided by delta y square. Okay. So, now we have to find the value of psi I n plus 1, which is the value of psi at the fixed point. So, for that now we will use the tangential velocity. So, what is tangential velocity? U is equal to capital U, because it is moving with a velocity u in the positive x direction. Okay. So, that means del psi by del y is equal to u. Okay. So, that you can now discretize using central difference. So, it will be psi I n plus 1 minus psi I n minus 1 divided by 2 delta y. Okay. So, this is your delta y and this is also delta y. So, 2 delta y is equal to u. So, you can write psi I n plus 1 is equal to psi I n minus 1 plus u 2 u delta y. Okay. So, 2 u delta y, psi I n plus 1 is equal to psi I n minus 1 plus 2 u delta y. Now, this value you substitute in the omega expression and find the omega I n. So, omega I n will be, it will be minus, so psi I n plus 1 is equal to psi I n minus 1 plus twice u delta y, okay, minus twice psi I n plus psi I n minus 1 divided by delta y square. Okay. So, now you can see psi I n minus 1, psi n minus 1. So, it will be 2. So, you can write omega I n is equal to minus 2 by delta y square. Okay. So, it will be psi I n minus 1, okay, plus psi I minus psi I n plus twice u, u into delta y, this term u into delta y, 2 we have taken outside. So, it will be 2 into delta y. Okay. So, along this top boundary, so the value of omega will be with this expression, okay, where u is the lead velocity. Now, you have seen that to solve the vorticity transport equation, we could derive all the boundary conditions for omega as well as psi we have already found. So, psi for all the boundaries okay. So, psi we have found. So, it is I is equal to 1 to I is equal to m and j is equal to 1 to j is equal to n. Okay. So, you can see that now for psi is 0 in everywhere. So, it will be psi 1 j is equal to 0 psi. So, it is for the left boundary, left wall, okay, psi. So, this is your m. So, psi m j is equal to 0 for right boundary, right wall, psi I 1 is equal to 0 for bottom wall and psi I n is equal to 0 for top wall, okay, for all I. Okay. So, these are the discretized boundary condition for psi, and also we have shown the discretized boundary condition for omega. So, you have the discretized equation for the interior points. With these boundary conditions, you can solve using some linear solver and you will get the values of psi and omega for this lead driven cavity problem. But you have to remember that psi and omega are coupled, because when you are solving the stream function equation you have omega, and when you are solving the vorticity transport equation you have psi. So, together this you have to converge and get the solution. So, in today's lecture we will show later the computer code for this problem lead driven cavity, and later we will show the results for this lead driven cavity and plane Poiseuille flow. So, now let us consider plane Poiseuille flow, where the flow is taking place between two infinite parallel plates. So, let us consider another problem, flow between two parallel plates. Okay. So, this is your flow between two parallel plates. Okay. So, we are considering two plates. Okay. These are two plates parallel to each other. Okay. Parallel to each other. Let us say that length of the plate is L and height is H. Okay. And if you, this is your domain, okay, this is your computational domain. Now, obviously on the wall velocities will be 0. So, that means if in terms of velocity if you give, so on the bottom wall u is equal to v is equal to 0, on the top wall also u is equal to v is equal to 0. Okay. And let us say that you have a uniform velocity inlet at the inlet. Okay. So, this is your inlet. So, you have a uniform velocity. So, this is your uniform velocity inlet. So, this is your capital U. Okay. So, capital U with this velocity it is entering. So, now you can see that boundary layers will be developed, okay, over the plates, and you will get a fully developed flow, okay, after a certain distance. So, and obviously you will get a parabolic profile at the when it will become fully developed. So, now numerically we will solve this problem. So, we are not considering plane Poiseuille flow where we consider two infinite parallel plates, and the assumption is that you have fully developed flow, but here it is a initially it will be a developing flow, after that it will become fully developed. So, at the outlet now we will consider the gradients of velocity will be 0, because the flow whatever it is going, we are assuming that it is a fully developed, and whatever way it is coming it will go out. So, that means at the outlet we will consider del u by del x is equal to del v by del x is 0. Okay. So, it is a fully developed condition, and this is your at the outlet. Okay. So, it is outflow boundary conditions, okay, outflow boundary conditions. So, inlet u. So, and let us say that you have I is equal to 1, I is equal to m, and here j is equal to 1, j is equal to n, and obviously your let us say coordinate is here. So, it is your x and this is your y, okay, this is your y. Okay. So, the outflow condition is fully developed. So, we have written del u by del x is equal to del v by del x equal to 0, because x is along the flow direction. So, now you can see that psi value again we can consider some constant value on the bottom wall. So, psi is C 1 on bottom wall. Okay. So, that you can find from the normal velocity. Okay. So, normal velocity is v is equal to 0, that means del psi by del x is 0, and so del psi by del x is 0, that means psi will be constant along x. So, psi is equal to C1. Okay. And for simplicity let us say psi is equal to 0 on bottom wall. So, you can take any value, right, because it does not matter. Okay. So, whatever value you will consider on the bottom wall, accordingly you will get the psi on the top wall. So, now we have to find what is the value of psi on the top wall, but anyway from the normal velocity condition you can find that psi will be some another constant C2 on top wall, okay, on top wall, because that will be also constant, because from normal velocity v is equal to 0. So, obviously del psi by del x is 0. So, along this x direction, so psi will be constant. So, let us say psi is equal to C2 on top wall. Okay. Now, how we will find this constant? So, now you know the inlet velocity u, from there you can consider that how you can find the C2. So, now you can see that what is this condition. So, you have the on the left wall you have u is equal to capital U, which is your normal velocity. That means del psi by del y is equal to u. Okay. So, that means you can write, okay, you can write that del psi is equal to u del y. So, if you integrate it, okay, from 0 to h, then you will get. So, if it is psi 1 and this is your psi 2, if it is psi 1 and this is your psi 2, then you can get that psi 2 minus psi 1 is equal to u into h, okay, u into h. Okay. So, h is, so y is varying 0 to h. So, it will be h minus 0, let us say. Okay. So, that means psi 2 will be psi 1 plus u h. Okay. So, the psi 2 value we have found. So, psi 2 is equal to psi 1 plus u h. So, if you consider psi 1 as 0, then psi 2 will be psi 2 will be u h, okay, for psi, considering psi 1 is equal to 0. Considering psi is equal to psi 1 is equal to 0. Okay. So, in terms of discretized boundary condition, you can write psi. So, on the left wall, bottom wall, so bottom wall is psi 1 is equal to 0, we have assumed. So, psi 1 is nothing but, so I is equal to j is equal to 1. So, psi I, it will vary from 1 to m, this is equal to 0, and top wall, okay, top wall psi will be psi I, j is equal to n. So, it will be u into h, u into h, or you can write psi I 1 plus u into h. Okay. So, for a given flow inlet velocity u and the distance between two parallel plates h, you can find the value of psi I n. Now, we need to find what is the value of psi on the left wall. Okay. So, left wall you can find from the integration of this equation. Okay. So, that means you can write psi, okay. So, I is equal to 1. So, psi 1 j is nothing but psi 1 j minus 1 plus u into delta y. So, delta y is the grid point. So, you can see, so it is your left wall, left boundary, inlet boundary. So, you have, this is your, if this is your 1 j and this is your 1 j minus 1. So, you can write, so from this integration you can write from here, okay, you can write psi 1 j is equal to psi 1 j minus 1 into u delta y. Okay. So, we have used first order scheme. So, you can see del psi by del y. So, del psi by del y is, we have written psi. So, you can write here also del psi by del y is equal to u, that means psi 1 j minus psi 1 j minus 1. Okay. So, backward difference we have used, okay, we have used backward difference, and distance between these two points is delta y. So, is equal to u. So, you can write psi 1 j is equal to psi 1 j minus 1 plus u into delta y. Okay. And on the outlet boundary, so at outlet what you can write for the psi value, outlet, okay, outlet boundary condition. So, this you can actually find from this equation only. So, you can write psi I is equal to m, mj is equal to psi mj minus 1 plus, okay, if you know the value of u, so then you can find u, okay, small u. So, you have to find at which point, at m j, okay, into delta y. Okay. So, this way also you can use, but better condition is that it is a fully developed. So, del psi by del x also will be 0. So, that you can write, okay, del psi by del x is 0. So, del psi by del x is equal to 0. So, del psi by del x is 0. So, you can write psi. So, j will vary So, it will be psi j will vary. So, it will be m j is equal to or minus psi m minus 1 j. Okay. So, if you use first order, so it will be delta x is equal to 0. That means, psi m j will be psi m minus 1 j. So, it will be easy to use this condition. Okay. So, this you can use psi m j is equal to psi m minus 1 j. So, we have found all the stream function boundary conditions, okay, in all 4 boundaries. Okay. So, on the bottom wall we have considered some constant value of psi, that is 0. So, you can see here, okay, and on the top wall you can calculate from the given inlet boundary condition and the distance between 2 parallel plates. Left wall you can find from this relation, and outlet it is easier to use this one. So, you can use psi m j is equal to psi m minus 1 j. Now, similarly you can find the boundary condition for omega. Okay. For omega, so if you use, so say bottom wall and top wall, it will be almost similar whatever we have derived for the Lid-Debye cavity. Okay. So, this is your parallel plates, okay, and you have inlet velocity u, and this is your I is equal to 1. So, this is your I is equal to m, and j is equal to 1, and j is equal to n. Okay. So, for the bottom wall, okay, you can write the similar way. Okay. So, you can see which way we have written for the bottom wall. So, bottom wall obviously the no slip condition. So, B will be 0. So, this equation you can write, okay. Omega I 1 so you can write omega I 1, sorry, it is bottom. So, it will be, so bottom wall will be omega, so j is equal to 1. So, I 1 it will be minus 2 by delta y square. So, it will be psi I 2 minus psi I 1. Okay. So, this is your omega boundary condition, same as the earlier. Okay. And for the top boundary, so top boundary also you can write similar way, only so top wall will be omega. So, j is equal to n. So, I n is equal to minus 2 by delta y square, okay, and you will get psi I n minus psi I n minus 1. Okay. So, omega I n you can find like this. Okay. Now, outlet boundary. Okay. So, outlet boundary we will consider, at outlet boundary we will consider fully developed flow. Okay. So, if it is a fully developed flow, you can write del omega by del x is 0. Okay. So, del omega by del x is 0. Okay. So, it is a fully developed condition. So, del omega by del x will be 0, and you can use first order accurate scheme. So, it will be omega m j minus omega m minus 1 j divided by delta x will be 0. So, that means psi omega m j will be just omega m minus 1 j. Okay. You can use also second order one sided difference also. So, but we have used for simplicity the first order accurate method. So, you can write omega m j is equal to omega m minus 1 j. What about the left boundary, inlet boundary? Inlet boundary. Okay. So, similarly for inlet boundary, so your u is capital U, okay, normal velocity. So, you can write del psi by del y is equal to u. Now, you can take the derivative. So, it is u is equal to constant, right. So, you can write del 2 psi by del y square will be 0. Okay. So, as you have a constant velocity inlet, so del 2 psi by del y square will be 0. So, from the vorticity equation omega is equal to minus del 2 psi by del x square plus del 2 psi by del y square. So, you can put del 2 psi by del y square 0. So, omega is equal to minus del 2 psi by del x square. Okay. So, now you can discretize omega. So, it will be I is equal to 1, right. So, 1 j is equal to minus, so it will be psi so if you take a fixed point, okay. So, this is your fixed point and this is your interior grid separated with a uniform step size, sorry, delta x, this is also delta x. So, this is your 1 j, this is your 2 j and this is your 0 j. Okay. So, you can write psi 2 j minus twice psi 1 j plus psi 0 j. Okay. So, psi 0 j we do not know. So, you can find from the tangential velocity. So, that means v is equal to 0. Okay. So, that means del psi by del x will be 0. Okay. So, if it is del psi by del x is 0, then you can write psi 2 j minus psi 1 j divided by del 2 delta x is 0 and that implies, sorry, psi 2 j by psi 0 j, psi 0 j. So, distance between these 2 points 2 delta x. So, it is 0. So, psi 0 j is nothing but psi 2 j. Okay. So, that means omega 1 j will be minus 2 by delta x square, okay, 2 delta x square. So, it will be psi 0 j you put as psi 2 j here. Okay. So, you will get psi 2 j minus psi 1 j. Okay. So, now we have found the boundary conditions for omega in all boundaries, okay, and in discretized form we have written. Thank you.